Sorry?
Yeah, I cannot put them full screen because otherwise I'd lose screen sharing. So we will have to go with the top bar still visible on the screen.
But this is fine. Then can you continue? Good morning. I would like to welcome Damiano from the University of Genova. Please go ahead.
Okay. Thank you for an introduction. Thank you for the other organizers for inviting me here for the second time. And as you can see, the talk is about Gaussian Quantum Markov Semigroups, and in particular, the Decoherence-free subalgebra of such kind of semigroups. As you can see below the title, this is a talk based on Fagnola and Professor Agredo. That can be viewed on the archive. The plan of the talk is to, at first introduce what Gaussian Quantum Markov Semigroups are, some foundation and some and some explanation of why are they called like they are, and then proceed into the Decoherence-free subalgebra. I will try to be as self-contained as possible. Many things have already been introduced by Professor Fagnola on his talk on Monday. So what Gaussian Quantum Markov Semigroups are? We start with some foundations, some mathematical foundation, in particular, so on the Hilbert space we are working on. This is standard in the quantum field. This is the bosonic Fock space. It is called like this. One can see it as the tensor product of many Fock spaces, one modal Fock spaces. But maybe the most intuitive way of seeing this space is to use this canonical orthonormal basis, which is also called the counting basis, and depends on a multi-index alpha, and each entry in the multi-index is actually the number of particles in the system that are in a certain mode. So the dimension of the complex space enumerates the number of modes that there are in the system, and we then have annihilation and creation operators that are naturally introduced as the operators that annihilate or create a particle in a certain mode. For example, the annihilation operator is basis lowers the particle number in mode J, or similarly, the creation operator raises the particle number in the mode J. And due to the coefficients that appear in front of the basis, these are unbounded operators. And so one of the themes that we see during the talk is the fact that we are dealing with unbounded operators. Another important properties of these operators is that they follow a certain commutation rule, and also commutation and non-commutations are another important theme during the talk, and also annihilation creation operators satisfy a certain adjunction rule. Then we consider the evolution on this system. We consider it as an evolution of an open system. We will see how it plays an effect later. But for now, the evolution is given on the bounded operators on the Hilbert space via quantum Markov. Very Professor Fagnola in his talk on Monday, but just a of maps that are weakly star continuous, that have some positivity conditions, and so on, and that describe the evolution of an open quantum Markov system, open quantum system. When we consider some stronger continuity of the semigroup, we obtain a generator, an infinitesimal generator that has this characteristic GKLS form, which is the one you see below, and then depends on two operators. So when they're continuous, so stronger, then we can identify it simply by choosing an operator H, which is self-adjoint and bounded, and a set of operators L, which are called Krauss operators, again bounded operators. But if we expand our view and consider also general quantum Markov semigroups, not only non-continuous one, then H and L can also be not bounded. And this is what we want to do. We want to choose H as our unbounded operators and L, which are linear polynomials in AJ and AJ daggers. So can we even do this? Can we, with this choice of operators, introduce a quantum Markov semigroups? Well, this is the case. Professor Fagnola showed in details his construction on Monday, but the idea is to choose a weak formulation for the generator, namely making it act on these elements psi as linear combination of elements of the basis, where all the calculation can be performed, all domain problems disappear, and one can actually define a quantum Markov semigroup. So which is the definition of a quantum Markov semigroup, of a Gaussian quantum Markov semigroup? We choose H, as I anticipated, as a quadratic polynomial in AJ and AJ daggers. Here there are also appear the coefficients we are choosing, and the only condition of on these coefficients are those such that H is at least symmetric, a symmetric operator. And DLLs are linear polynomial in AJ and AJ daggers, and so these are their expressions, and the condition we make on their coefficient is such that the set of Krauss operators is linearly independent. So there cannot be, it's linearly independent. You know what it means. The theorem is that we can construct a unique quantum Markov semigroup starting from a generator with this choice of operators, and this is called the Gaussian quantum Markov semigroup associated with H and LL. So this is how we define a Gaussian quantum Markov semigroup. But why are they called Gaussian quantum Markov semigroup? Well, the idea starts from looking at Gaussian states, and the whole point of this slide is to convince you, or at least give some intuition on why these states are called Gaussian. And the main point is that they are as similar to classical Gaussian random variables as we can. And the way one sees this is to consider at first while operators, which are they have a very important names, and they are very used and wide and important in this field, and we can see them as exponentiation of a suitable linear combination of AJ and AJ daggers. And we say that rho is a Gaussian state if this quantity, which depends on rho and on the while operators, is the function as this expression. And the first thing that one notices on this expression is that it depends on two things. The first is a vector, omega, which is called a mean vector, as the mean of a classical Gaussian random variable, and S, which is the covariance operator, as the variance-covariance matrix of a classical random variable. To further convince you of this fact is the real part that appears in front of the complex scalar product means that we are considering the real space associated with C to the D. And if we exploit this, the isomorphism between C to the D and the real number to the 2D, that is decomposing Z into its real and imaginary part, then we see this, we obtain this expression that you see at the end of the slide. And this expression is precisely the characteristic function of a classical Gaussian random variable. So this is why these are called Gaussian states, but to us, they are as similar as Gaussian random variable as possible. And the point here is that if we start from a Gaussian state, then our semigroup that acts on states in this way still yields a Gaussian state. So in some sense, Gaussian semigroups preserve the set of Gaussian states. And moreover, we can give the explicit evolution of the mean and the covariance operator. operator, which depends on some real linear operator that depends on the parameters of the semigroup. But the main takeaway point is Gaussian semigroups preserve the set of Gaussian states in its entirety. Another important property is that they satisfy this evolution rule, meaning we can find explicit expression for how they evolve while operators, meaning they give another while operator and multiply by a constant. And our result we managed to prove was that all these facts are actually equivalent and can be used independently to define a Gaussian quantum Markov semigroup. Namely, a Gaussian quantum Markov semigroups can be taken, as I introduced to you earlier, as a certain quantum Markov semigroup associated with the choice of HSE-NN. Or we can define a Gaussian quantum Markov semigroup as a semigroup that satisfies this explicit action on while operator for some suitable C, Z, and zeta, the parameters that appear in the coefficient. Or eventually we can define a Gaussian quantum Markov semigroup as a semigroup whose produal preserves the set of Gaussian states. So these are three defining properties of this set. Moreover, these semigroups have been used in the literature, have appeared there also as under the name of quasi-free semigroup. So they are really actually important, and one can study many things. We have actually also already started studying many things. The one I want to present to you is related with the decoherence-free subalgebra. So let me first say what the decoherence-free subalgebra is and why is it important to study. And the definition of a decoherence-free subalgebra is the set NT, which collects all the elements of the boundary operators that satisfy this multiplication rule, one would say, when looking at the semigroup. And, well, why is this set important? Why are we interested in such a set? Well, this proposition should at least clarify some motivation for this, since by using this definition, one can prove that NT is actually the biggest von-Neumann subalgebra of B of H. So it's a subalgebra closed for the weak or the strong topology, such that TT acts as a star homomorphism on it. So this property, these multiplication properties, when looked on NT, is actually guarantees actually a star. So NT is a set on which the QMS acts in a nice way, one could say. And maybe even more remarkable is that whenever we look at the action of the semigroup on an element of the decoherence-free subalgebra X, then the explicit action is the one you see below. And the thing to note is that there is no dependency on cross operators. There's no dependency on the LL. And this very evolution is the same that one would get if we looked at the system not as an open system, but as a closed system, when the only relevant operators that describe the system is the Hamiltonian. So this evolution is the same that one would get whenever considering the system as a closed system, as a closed quantum system. So the decoherence-free subalgebra is the algebra, it's the biggest one of subalgebra. And on the decoherence-free subalgebra, we do not have dissipation, we do not have decoherence. And this is one can understand this by looking at this formula, because it is the same formula as that one will get when looking at a closed system. Okay. Moreover, apart from this intuition, one would also get that the decoherence-free subalgebra allows one to understand many properties, also in asymptotic properties of the semigroup. By looking at the decoherence-free subalgebra in relation to the fixed points of the semigroup, or by requiring that the decoherence-free subalgebra has some expression, specific form, then one could also infer some further properties on the semigroup. So it is an object that is being widely studied and has some really interesting uses in the theory. Now we would like to characterize it, and understand how the Decomposition subalgebra of a Gaussian Quantum Markov Semigroup is made. And the main result we will use is this theorem from Professor Fagnola and collaborators that we also proved in a different way in the paper I cited you at the beginning. And it asserts that the Decoherence-free subalgebra can be identified by looking at the generalized content of this set of operators. So instead of looking at how the semigroup explicitly act, which is not always easy, and in general it's actually difficult to do, one looks at this set of operators that depend only on the operators in the generator, and computes the generalized content. First of all, let me say generalized content means is like the extension of the content that also takes into account the fact that we are dealing with unbounded operators. So that commutation should not only refer to switching the position of the operators, but also takes into consideration the domain of these operators and the fact that they can pose problems when looking at composition of the operators. Apart from that, we now have this set. We need to compute this set and then compute its generalized content. And the idea here is that for Gaussian quantum Markov semigroups, all the operators that appear in polynomials in AJ and AJ dagger, because both H and LL are polynomials in AJ and AJ daggers. But when explicitly looking for this polynomial, starting from n equals 0, one gets LL and LL stars, which are, by definition, first-order polynomials. When looking at n equals 1, one gets the commutation or the commutator of H with LL or with LL star. And by commuting a second-order polynomial and a first-order polynomial, one still gets a first-order polynomial. And so one can go on, because when looking at n equals 2, one obtains again a commutation of a second-order polynomial and a first-order polynomial. And again, this is a first-order polynomial. So all the operators that appear in this set are first-order polynomials. And this allows us to use this result and infer and evaluate and characterize the Decomposition subalgebra of Gaussian quantum Markov semigroup. The idea, let me briefly discuss it, is that we can further simplify the situation by switching from looking at operators, which are linear combination of AJ and AJ daggers, by simply looking at their coefficients. So we can further transform the set of operators in a set of vectors in C to the 2D. In particular, in the set of vectors, we can find creation and liquidation operators by looking at the elements of the canonical orthonormal basis, but also all the iterate commutators, this one, also can be looked at as vectors in C to the 2D. So the first part, the construction of the Decomposition is looking at a set, which let me show you, was this one, that uses the explicit action of the semigroup. Then one can instead look at the set of operators and compute the generalized content in order to compute the Decomposition subalgebra. And what we are now doing is that, well, this set of operators is actually just a set of vectors in C to the 2D. And we call this set V, the one you see below. Now, how can we transform then the commutation requirement to compute the Decoherence-free subalgebra? This is done in like loose terms. I would just try to convey the idea instead of looking exactly at the proof. We can now decompose C to the 2D into 3 spaces. And these spaces corresponds morally, at least, to the first one, if by looking at linear combination of elements in V, we can recover both AJ and AJ plus D, so both annihilation and creation operators. Or on the other side, we have the subset of C to D to D, where we do not have neither EJ nor EJ plus D in V, so neither creation nor annihilation operators. Or a set in between where we have one but not the other. And this allows us to look then at the set of iterated commutators as three disjoint subsets. And this idea is, of course, not really precise because one cannot always hope to have this nice situation. One has to consider to be more in the, this is like asking for a linear subspace to be always aligned with the canonical orthonormal basis, which is not always the case, of course. And to account for this, one needs to make some transformations that are doable. I will not show them to you, but one then needs to transform C to D into, again, a subset of CD where where we have the standard symplectic structure. And symplectic here is just a synonym for the commutation rules. So an algebraic structure that encodes the commutation rules into CD. And now we can make the decomposition with precise. So the first set, the one where we have both annihilation and creation operator, is the biggest symplectic subspace in M. Or the set where we don't have either neither annihilation nor creation operators is the biggest symplectic subspace in M prime, which is the complement of M. And the set in between is what remains, is the intersection of the two. So why have I done this introduction? Well, because the main result for the Decoherence-free subalgebra is this one. We can say that the Decoherence-free subalgebra is the subalgebra, of course, generated by Weyl operators. So this is already a nice property. The Decoherence-free subalgebra is generated by Weyl operators, but not all Weyl operators, just the one where we take their argument in the symplectic complement of M. And the symplectic complement of M, I did not show you earlier, but it is composed of MC and M2 terms in the decomposition. And using this decomposition, we can actually find that up to unitary equivalence, so up to unitary transformations of the space, the Decoherence-free subalgebra is always a tensor product of two factors. The first one, that depends on MC, is commutative, is classical. It's the L infinity function of from R to the DC to C. And here DC is exactly the real dimension of the set MC. Eventually, the second factor is instead a full factor, non-commutative quantum factor, and its dimension depends on the dimension of MF, which is or half the dimension of MF, to be precise. Okay, so this is the main result of my talk, and I can stop here. So thanks for your attention.
Thank you very much for your talk. So, are there any questions? Please feel free to ask questions.
Well, may I ask a question? If it's possible to somehow understand why there are some blocks of B of C to some powers. So, as I understand your previous slide, yes, you have only classical or quantum without blocks in some sense. So it's just why there are no some transient things. Is it possible to understand it? Sorry, just possible to understand by proof?
Well, the way one can see this probably is that is through the decomposition I showed you earlier. So you have let me try and explain it in a more natural way. So you have you start by looking at the Decomposition Subalgebra as the commutant of this set, which is set of creation of linear combination of annihilation and creation operators. And by the nature of this set, which is self-adjoint, the Decomposition Subalgebra can be generated by Weil operators. Okay, so this is the fact. So this linear combination of annihilation and creation operators can lead you to quadratures and therefore to Weil operators. And now the point here is well, what do you start looking at commutations of operators with quadratures, and you know, if the set was only composed of a quadrature, then all the bounded function of that quadrature, the very quadrature, would commute with it. Okay, so you contain an L infinity. And on the other hand, if I'm to explain it to you. Let me say the fact that the algebra is generated by Weil operators, which is the starting point for this theorem, allows you to, in some sense, diagonalize the Decoherence-free subalgebra, because by some transformation, which is a Bogoliubov transformation, a symplectic transformation, you can separate the two factors, and a priori they can be like interconnected. So you can have you can mismatch annihilation and creation operator and have the Decoherence-free subalgebra, which is not like nicely factorized in this way, but you, by a symplectic transformation, so by a unitary Bogoliubov transformation, one would say, you can always separate these two factors. I don't know if I.
Okay, I think I understand. Thank you. Thank you.
Right, you're welcome.
Are there more questions? Okay, no questions. So then thank you again for the talk. And before we can go to the lunch break,